Hi folks, this is the second video tutorial that I'm doing to solve a single degree of freedom vibration problem in Catia V5. Now, Catia is not necessarily the best software to solve problems of this type. However, since I was teaching the vibrations course, introductory vibrations course, and the students already knew Catia and they had already taken a course in doing finite elements with Catia with me, I thought it was the right place to show them how to solve very simple problems of vibrations using Catia. These are not well documented in the Catia's help documentation, and therefore pretty much it's the only resource at this point. Now, I already did a problem of this type, exactly the same problem. The only difference was that the load that is applied to the mass was actually a suddenly applied constant load, which still makes the problem dynamic. However, we want to do this thing right now where the force is not constant, but it's changing with time. So something like that's called harmonic response of a single degree of freedom system. And we usually do this type of thing analytically in a vibrations course. So let me just shed some light on it. First of all, the data is given here, K, C, and M. And the amplitude is supposed to be 10 Newton, and the driving frequency is 1 radians per second. Now, the natural frequency can be easily calculated. It's 0.225 hertz, and there is a damping ratio of 17% here. And the solution to this problem can be written as the transient part, which is over there, plus the particular part. Now, the particular part, I've written it as the Duhamel integral, or the convolution integral. In this particular problem, it's possible to guess this thing, and the approach is going to be the same thing. So Duhamel integral, that means that you take the forcing function, replace it with sine f0 sine omega t, and do the integration patiently, and you're going to get this solution, okay? And notice that for the data that's given, this whole thing reduces to that expression. And if you plot it, in the absence of damping, okay, this does not involve damping. I'm assuming this is an undamped solution. Then it's going to be something like that, okay? Now, if you want to do damping, there is a lot more to it. You have to do the integration by parts, etc. So I haven't done that. I will show you the results in Catia only. Now, these slides are put here, these next two slides are put here because it shows me the steps that I follow in order to go from the initial point all the way to where you want to plot the displacement. And here's the second one. Now notice that unfortunately, if we want to do a simple spring system, mass spring system in Catia, you have no choice but to actually create some kind of a regular element. Now I've chosen to do beam elements, and therefore without having an element, you won't be able to define the stuff that's needed to basically describe the spring and its stiffness, etc. So you'll see what I mean. I already did this thing in video 1, but it's kind of hard to believe that people will say, why are you creating beam elements if you're not going to be using it? Well, unfortunately, if you don't do it, then you can't define the spring element either. Now, there are other packages that allow you to define discrete elements such as dampers and springs and things like that, but not here. Okay, so let's go ahead and create 2 points, and these 2 points, the spring is going to go between these 2 points, but when I create these 2 points, I also create a line in between them so that I can mesh it later on with beam elements. Okay, so let's create 2 points. This is going to be the wall, and the next one is going to be 1 meter away, 1 meter away, and it's going to be the other end of the spring. You can see that right there. And then I create a line going from this point to that point. Okay. And we apply a dummy material to this. Now the dummy material under metal I don't think there is a generic material that I can define here. Let's see now. Some software have a generic material that you can put anything you want. But I'm gonna put a dummy material aluminum on that. But I will go and change the properties of aluminum. The under the analysis tab, the Young's modulus 70 gigapascal. What I'm going to do, I'm going to make that thing 0.1 Pascal. Basically, I make it extremely soft, and the mass of it, mass density, instead of being 2700 kilogram per meter cube, I'm going to make it also 0.1. How about that? 0.1, which means that basically no mass. You can see that. See, these are changed. Double click, analysis tab. This is 0.1 Pascal, and this is 0.1. We don't want these numbers to influence the stiffness of the spring that we're going to define or overwhelm it, and therefore change the frequencies. All right, we're going to do this thing in 2 steps. Well, first of all, let's go to generative structure analysis. We're going to do this thing in actually 3 steps. First, we do a static analysis to sort out any mistakes, possibly, but we also need the load that we're going to put in this static step later on, okay? So, and then we're going to insert a frequency step, and finally, transient dynamic step. Okay, so let's see now. Let me hide these points first, so that I don't inadvertently put a restraint or a force on these points. You have to put it on vertices, basically. Now, let's mesh it here. Here's the model manager. You click on it, click on the beam. The only beam element that's available in Catia is a 2-noded beam element, and you can select this. And it doesn't matter what the size of the elements that you put in here. If you say minimal mesh, it overwrites that, and it just takes the smallest number of elements from one end to the other end. So I say minimal mesh, basically it's going to put 1 element. If I had used 0.5, it would have put 2 elements here. But 1 element is good enough, okay? Now, we need to specify the cross-sectional properties. So for example, click on the 1D property, and this is the support. Okay, cylindrical beam and cross-sectional radius of 0.1. Now these are totally dummies, but they're needed, so I'll just leave it the way it is. So 0.1, and then say okay. Notice that we can close this because this is a circular cross-section, doesn't need an orientation point, and I can close it. Okay, good. Now let's clamp this in. So we're going to clamp this in. And then this point, we're going to assume that it does not move in any direction and rotate in any direction, but move only in the translation, only in the y direction. So user-defined restraint on this point, everything is fixed except for translation in y. And the reason I do this is that I want to make the problem a single degree of freedom system. Okay, if I let it, for example, move in other directions, etc., you'll get frequencies which are going to be associated with bending and torsion and things of that nature, which I don't want it. Okay, I just want a translation on degree of freedom, single degree of freedom. Now, let's put a load here, a force. Here's a force, distributed force at this point in the direction y, 10 newtons. Now, if I run this problem, there's a spring here with a stiffness of K. There will be, actually, it's not yet. There will be a spring of stiffness 4, and the force is 10 newtons, so the deflection is going to be 2.5. That's how I'm going to measure whether I've done things correctly. Okay, so what we need to do in order to define the spring, I have to go and create a connection here. See that general analysis connection between this point, this endpoint, and for the second component, this endpoint. Okay, so it creates a connection, and it's right here in the tree. You can see that. And then I click on this user-defined. Let me move this thing out of the way. User-defined distant connection property. It says, what is the support? The support, the only thing that you can pick is actually this connection that you created. You can't select anything else. just this, either from the tree or from the screen. And you have choices. You can do rigid springs rigid, or you can do spring rigid, or you can do rigid spring, etc. It makes no difference. And you click on the wrench to specify the stiffness in the direction Y of this spring. Direction Y, because this is the global direction. The spring is aligned in the Y direction, and therefore 4 newtons per meter in the direction 2. Good. Now, if I run this, I better get 2.5 as the 2.5 meter as deflection of that point. So you click on it, run it. Okay, and then you look at the deflection, 2.5. If you had used for the Young's modulus, for example, of aluminum, you had used, I don't know, maybe 1 instead of 0.1, maybe this would be a little bit different. It won't be that. It won't be 2.5, it'll be 2.49 or something like that. But that's fine. Now, the next step is to actually insert a frequency step. So insert a frequency step. And for the restraint, I use the restraints that are used in the static case right here. See that? I can select this, which I clamped that and then made this thing, just move in the Y direction. And then we say OK. And obviously, I have to put a mass here at this location. So for the mass, you go to the mass toolbar right there. Okay. Let me see exactly what the title of this thing. I'm pretty sure it says masses. Yeah, masses. The first icon. It says, where is the support? It's that point. Notice that if you go close enough, you see that something like a mass is put in there, and 2 kilograms. That's what the problem said. 2 kilograms right there. Okay. Now we say okay. Now all you have to do is to run it. However, you see that it comes back with an error message. I'll show you what it says. Okay, it says, look, you have only 1 degree of freedom. Why are you asking for 10 degrees of freedom? Because if you go to the frequency case that we inserted, and if you double click on this, notice that I'm asking by the default value of 10 frequencies extracted. Now this guy doesn't have 10 frequencies. It's a single degree of freedom. There's only 1 frequency. So let me change this thing to 1 and then run it again. No messages then. Plot the deflection and double click on it to get the frequency. On the occurrence tab, 0.225 hertz, which is exactly what we calculated here, 0.225 hertz. Okay, good. Now that we have extracted the frequencies, all the frequencies, we're going to say, okay, insert transient dynamic response case. You click on it. It says, okay, where is the reference frequencies that you extracted? Well, the only thing that you can pick for the references is this thing that we extracted. Nothing else can be picked, but just this. So you have to have a frequency case first. Okay, we say okay, good. Now, as for the load, in the first tutorial I showed you that load was constant as a function of time. Here it's not. So what we need to do is we have to create a time modulation. Now, time modulation is a fancy way of saying create a spreadsheet, first column being time, second column being the amplitude or the variation of the force as a function of time in a non-dimensional manner. So I don't have that. I have to go and create an Excel spreadsheet, which I have it here. So the first column is time. I'll put an X. X means I'm representing basically time. This is the x-axis, the time. And for the second column is non-dimensional property, non-dimensional amplitude. So I just y, nothing, parentheses, nothing between and close the parentheses. So let me start with 0.1, 0 and 0 point, and go all the way to 40 seconds. So I have to drag this thing until we get 40. Let's see, where are we here? 40 seconds. Where are we now? Let's check it out. We are over at 11. Let's go further. 32. You know, you need to find the time until you, I mean, during a duration that which you're interested to do the simulation. Okay, so if you're not interested to go all the way to 40 seconds, then go wherever you want. So here, okay, so let's say around 40 seconds. And now the amplitude. The amplitude is, yes, it's F naught, but F naught is 10. So all I have to do is to non-dimensionalize the non-dimensionalized value. So this is equal to, the driving frequency is 1 sine of omega t, but omega is 1. I don't have to write it. There is time. Close this thing. Hit return. Needless to say, you're going to get 0. Sine of 0 is 0. And then drag this all the way to the 40 seconds that we have here. So we have created the time modulation. And then we can kind of do the rest of the problem. Right there. Good. So we save this. We can close it or we can leave it open. It doesn't matter. As long as you save it, it doesn't matter. You go here. And now you click on the load excitation. Double click on this. Notice it says, what is the load? The load is that static load that I put in there. That's the only thing that I can select. That's this. Remember the 10 pounds or 10 newtons that I apply? And it says, where's the modulation? The modulation is in the tree, you have a modulation. Well, let's see, somewhere down here. Oh, I'm sorry. We didn't do that. Cancel. We click on it. You see that? Time modulation. It says go find it. Remember I created this thing? This is the one that I just created. Now we say okay. Now in the tree we have a modulation exported right there. By the way, you can have several of these, but this is the one that I want. So now go back to the load. It says what is the selected load? The selected load is that load that I applied 10 pounds here. That's the one that I applied, remember? And for modulation, I go and select it from the tree. It's this thing. This is a factor that you can take, you know, the stuff and multiply it by 5 or divided by 6, etc. In my case, I put the 10 pound there, and the amplitude is pretty much 1, so we get the right value. But if I had put 1 pound here, then I would need to either put a 10 there or go and change my Excel spreadsheet so that the second column is multiplied by 10. But this is, I don't have to do that here. Now that's pretty much it. The only thing is that if you go to if you double click on this transient dynamics, it says what's the duration of the simulation. We start at time 0, we go all the way to 40 seconds. And how many steps? The more steps that you put in here, the smoother the curve is going to be, but don't overkill it. Let's put 200 and see what happens. Okay, pretty much it. So put the cursor. We don't have to run on anything. The thing that was supposed to be run was the frequency case, and it is run already. Okay, so you put the cursor on this line, right click, it says generate 2D display. You click on it, and next, one graph, finish, and this thing pops up, and all it says, okay, you want me to tell you what point is moving by how much? You go and pick it. And this is why one of the reasons I had to mesh that beam, because I now have to go and select that node number 1. So if you minimize this thing and you go to the background, let me move the other way. I have to select this node, okay, this node. Now, if there are things that are blocking my view, can always hide them. But you need to get to this node. There's no other way. You have to get to this node, and then this is node number 1. You say add, and you close this thing, and notice that here a graph has been created. Double click on it, and there we are. Now a couple of things. Let me close that. If you put this is the amplitude, right? If you put the cursor there, right-click format. Now remember, these things we discussed in tutorial 1 also. Real. This goes between 0 and between positive and negative values. Okay. Now the other thing is that you might say, wait a minute. Although the pattern is the same as that, but the numbers are not quite the same. Well, part of the reason is that automatically damping has been created. Now, if you say, well, how do you know that? Well, you go here and click on the damping. Catia, by default, if you click on the wrench, by default, it takes 1% damping on all the modes. So I'm going to make this thing 0 and look at the graph. Oops. Okay, I accidentally stopped the video, so I had to do a second part, and the second part is going to get joined to the first point and uploaded later. So I changed the damping to 0. Say OK. Automatically, Catia puts 1% damping in all the modes. So you say OK. Now say OK. And if you go to this 2D plot, you see that now the numbers are pretty much what you got here. Start at 0, go to almost 5, and then about -7, and then all the way to 9. So start at 0, 5, almost -7, all the way to 9, etc. So this actually is the same as that graph where damping is 0. Now in our case, the damping was 17%. So if I close this, I go here to damping, and instead of the 0 that I forced it to be, I make it 17.6 and say OK. I did it again. Okay. Say OK, 17.6 OK, and close this and double click on the 2D plot. You see that it's it's going to get damped. The solution, steady state solution, is here. Look, these heights are all the same. Okay, so this is the transient one that dies, and this is the steady state response. The amplitude, of course, is lower. The amplitude is lower than what you see here. Okay, what you see here, it goes all the way to 9, etc. But with that 17% damping, the amplitude is going to be constant, but it's going to be lower. And these are things that we do in a vibrations course. So good luck.